Oh. So the second example is used for the medical care. So it can be use the RF signal to monitor the sleep status or the fall detection for the elder people. And in the third example for human-computer interaction, so various signals can be used for gesture recognition and the VR interaction. Okay, so if we look back at the past over 10 years we see that the development of wireless sensing can be roughly divided into 4 stages. So at the first stage, at the very beginning, so we use the handcrafted physical features of signals. For example, AOA, TOF, something like that. So at the second stage, start from around 2017 to 2019, so along with the success of deep neural network in computer vision, so the wireless sensing community began to use these classic and successful models to use it in wireless signals and developed many solutions. And in the third stage is around 2020 to 2023. So we use some deep neural network models that specific designed for radio signals. So classic research works like SLNet and RFNet. So in recent 2 or 3 years, so the rise of generative AI models, so we use these generative AI models to develop RF-oriented generative models. Okay, so let's first look at the traditional sensing pipeline. So at the front end, so we collect signals and perform signal processing algorithm and get the signal features. So then we feed these features into discriminative models, such as geometric method like triangulation, trilateration, or conventional machine learning models like SVM or MLP. So finally, the model outputs a final result like the location or a label or some score. So this is the basic pipeline of traditional. Okay, next. So on top of this pipeline, so we can insert a generative model as a plugin. So here the keyword is as a plugin. So the most direct use of this plugin model is data augmentation. That is, so we know that wireless signal data are hard to collect and label. So it's also hard to generalize across environment and devices. So we can use the generative models to sensorize more training samples to train a model. So this figure shows the performance gains when we use generative model as a data augmentation plugin in different wireless sensing tasks. So here the sensing tasks include various tasks. For example, the gesture recognition, fall detection, gait analysis, activity recognition, and so on. So for wireless localization, using generative model for domain adapter or data completion, so can also significantly reduce locating errors. So this means that, so even without changing the overall pipeline, we just add a plugin here. So Gen AI can already serve as a powerful performance booster, so in many wireless applications. So if we go one step further and think it from the very basic perspective, so a generative model can also replace the discriminative models and directly used act as the unified solver for the task. So here the keyword is replace. So in previous slides, we see we use generative model as a plug-in, right? So here it can replace the traditional discriminative models. So for example, we can train a conditional generative model that take a signal sequence as an input and directly output generates a trajectory or a status sequence for localization and tracking and sensing tasks. So this slide shows some examples where the generative model is used as a direct solution. So for instance, in signal anomaly detection, channel estimation, and various coverage heat map construction, generative model often achieve better performance than traditional non-generative method. For these two aspects of the examples, we can say that, so whether as a plug-in or performance for performance enhancement or as a main solver for the task, generative AI has already shown its value in various applications. Okay, now I will follow the historical path of the various sensing development in the past decade and talk about the discriminative models and then the generative works in more details. Okay, let's first review what researchers have done in the stage from the physical features to the discriminative AI. So at the very beginning, so we analyze the signal by the handcrafted physical features. So classic research works like Spotify and VIDA. So here I say the human crafted features such as the AOA and the TOF. So AOA means the angle of arrival. So it directly gives the angle information. And TOF means the time of flight. So it directly gives the distance information. Right? So array track is a technology, so it uses the multi-antenna array to estimate AOA and design several strategies to mitigate in rich multipath environment to get the accurate AOA. And Spotify goes one step further. So it combines AOA and TOF, use multiple subcarriers to increase the effective number of antennas and thus improves AOA resolution. So besides angle and the distance, we know that speed is another important information. So research works like CALM and VIDA introduce Doppler frequency shift, short for DFS, as a new feature. So CALM analyzes the power distribution of DFS component to describe nearby human motions and use it as input to an HMM. So VIDA use the relationship between DFS, human speed, and the position to achieve passive tracking of a human's working trajectory. Okay, some follow-up work such as VIDA2 and MD-Track, they combine the AOA, TOF, and the DFS in a more integrated way. So by jointly use these three features, they can achieve more accurate localization and sensing and reach multipath conditions. So however, although these features can describe geometry very well, so they are very sensitive to the environment. So in VIDA 3, so we propose a feature for human action recognition called by body coordinate velocity profile, so BVP for short. So the key idea is here. So for the same gesture, if it is performed at different positions and orientations, so its speed distribution in the global coordinate system changes a lot. So, but if we can transform the velocity into the body coordinate system, so then the BVP patterns of the same gesture should be similar across different environments. So, patterns of the same chart should be similar across different environments. So the figure shows the changing patterns of the BVP. So, so here we also, let me see. So this slide compares the traditional used features, CSI, DFS, and the BVP, so in different domains. So the upper part of this chart is in domain 1, so the lower part is in domain 2. So here, a domain means the environment, positions, and orientations are all different for these two domains. So we can observe that the CSI waveform changes a lot between domains, although the gesture is the same, the action is the same. So under the DFS spectrum also changes with the scene, but the BVP patterns stay relatively stable across different domains. So we can conclude that in cross-domain settings, CSI and DFS, these features are very easy to change, while BVP is more stable and is more suitable as an environment features. Here I show more examples. So exhibit BVP examples of different gestures. We can say that so BVP is a distinct features to you recognize different gestures. So in the second stage, so move to the second stage. So with the success of the deep learning method, especially used in computer vision, so many accurate and robust recognition methods have been proposed. So inspired by this, so the wireless sensing community began to combine this classic deep learning method with the physical features we just discussed. So at the beginning, so many works simply converted the raw CSI and the CSI-based features into heat maps or with images and fed them into the recognition model as black boxes. So for example, VIDA 3 uses convolutional neural network and RNN, CNN, and RNN. So CNN extracts the spatial features and for BVP, and RNN models the temporal dynamics. So it can recognize 6 common human gestures with about 90% accuracy. So another work called YPulse take a 3D velocity spectrum as input in the and use CNN, so separate the pulse-related dynamics from static clutter and in the environment and the RNN to generate smooth skeleton motions. So in our work S4, we go one step further beyond the CNN and RNN. So specifically, we use spatial and temporal transformer blocks to fuse time frequency information in various signals and use video frames as supervisions during the training. So this cross-model supervision helps the wireless model learn more robust generalized features. So all these deep learning models basically treat the RF signals spectrogram as an ordinary image, as a normal image, and directly reuse the models developed for computer vision. So under this assumption, there is a problem. So these models do not fully exploit the time frequency structure of the signals or the physical meanings behind the signal processing algorithm. So we get into the third stage. So in 2023, our team proposed the spectrogram learning neural network, so SLNet for short. So it has two key design modules. The first one is the spectrogram enhancement network, SEN, so which addresses the spectral blur and the leakage problem. So the second one is the polarized convolution, so which address the problem that CNN are not sensitive enough to the spectral positions. So our motivation of SEN, the spectrum enhancement network, comes from a simple observation that, so we synthesize two chirp signals whose frequencies goes from 1 to 20 hertz, from 5 to 24 hertz. So ideally, if we plot their spectra with a perfect Fourier transform, so we should see two clean straight lines in the middle. So, but when we add these two signals together and plot the spectrum, we get a very messy picture on the right. So many components stick together and become hard to separate. This shows that in real conditions, different frequency components interfere with each other and severely blur the spectrogram. So behind this, there is a basic limitation of the frontier transform. So a Fourier transform. Fourier analysis, some signals are infinity long. So, but in practice, we only analyze finite length. This is a window size segment. So this leads to the spectrum leakage. So to handle this, we propose a neural network based on the method of spectrogram enhancement. So the input of this network is a blurred and leaked spectrum. And the output is the ideal spectrogram. So we first generalize ideal spectrogram with 1 to 5 frequency component. Then we simulate spectrum leakage and blur and use the pair of ideal and degraded spectrogram to train the network in this way. So the model learns to remove blur and leakage from observed spectrum. So, but removing blur is still not enough. So this is another structural issue from CNN itself. So we know that CNN is essentially a local pattern detector. So it assumes that a feature means a same thing, no matter where the feature it is in the image. So for convolutional image, this is good, but for RF spectrogram, this assumption does not hold. So let me give either example. So a face, no matter in top left corner or bottom right corner, is still a face. So and should be recognized as a face, right? So, but for spectrogram, however, the position carries physical meanings. So compare the left and the right. So left shows a face. So no matter the face appears in top left corner or bottom right corner, it's still a face and should be recognized or classified into the face class, right? So, but in a spectrum, however, the position carries physical meanings. So shift along the axis corresponds to changes in distance or velocity. So if convolution kernels are completely insensitive to the position, they may mix up the patterns that actually represent a different distance or speed. So we need a new network structure that keeps the strong local modeling ability of CNN, but reduces the translation invariance. So to achieve this goal, we propose a new idea: use phase to polarize the spectrogram. So we design a linear phase modulation so that nearby frequency components have a similar phase. So while far away components have very different phases. So in this way, each point in the spectrum is mapped to a polarized point in the complex plane. So it has a direction and also encoded position information. So it carries both local discriminative features and the global position information. So finally, we combine SEN and polarized convolution into a complete spectrogram learning network. So it is especially suitable for gesture recognition, fall detection, and activity recognition, where we need high frequency resolution. This is a video demo. Okay, with the features, with these features and RF-specific AI models, so we can already achieve very high accuracy in some common applications, such as the device mobility detection. Let me show these demos. The first one is the device mobility detection. So on the screen, so the left side shows the real scene, and the right side shows the user interface. So we configure a device with antennas and move the device itself. So because the transmitted and the received signal change, so you can see that the waveform of the right also change, and the indicator turns from green to right. So which means the device is detected as moving. So an important thing here is that, so if a person moves around the device and the system does not trigger an alarm, so it can distinguish the device motion from the environment changes. So the second demo is the human approach detection. So we connect two antennas to a network card and collect data. So when a user walks towards the antenna, and the indicator turns right and shows approach. So when the user stays for a while and then walk away, so the indicator turns orange and shows leave. So if the user comes from another direction of the system, can still recognize the approach and the leave events correctly. So the third demo is the fall detection. So at the beginning, after the system starts, the light in the upper right corner is green, which means there is no fall. So when the user suddenly falls down, so the light turns red and a fall is detected. So the light turns red. That means a fall event is detected. So we change the direction and repeat the experiment. The system is still recognize the fall. So you can say that the you can say that the normal working event will not trigger the alarm. So we also test different fall postures, and the system can still detect them. So to summarize, so wireless sensing has gone through several stages. So from the very earlier physical features to deep learning models reused from the computer vision, and then to RF-specific neutral network structures like SLNet. So in the demo application we just saw, so discriminative models can already achieve reasonably good accuracy. So naturally, question now is, what is the next step? So 2 years ago, we started to review the evolution of the CV and the NLP to see if we could learn something for wireless sensing. So we found that, so this field also experienced the similar path. So in CV community, so we had handcrafted features like SIFT and HOG at first, and then discriminative models like CNN and ResNet, and in recent years, generative models such as Stable Diffusion. In RLP community, so we moved from the bag of words, TF, IDF, to the discriminative models, RNN, and now the GPT-like large language models. So again, also from the handcrafted features to discriminative and then go to generative. So for RF signals, for wireless signals, so we have already passed the stage of physical features and the discriminative models. So we are asking, can we also build a generative AI models to handle, to processing RF signals? So this idea has a basic in cognitive neuroscience. So the cognitive neuroscientist Andy Clark proposes that the human brain is essentially a prediction machine. So the brain uses an internal generative model to predict the state of the outside world. So in other words, when an intelligent agent can generate the future changes of the environment, it starts to show a primitive understanding of the world. So in CV, this is called the word model. That is for a video sequence. So if you can predict the next frame based on the existing frames, so that is you understand the rationale behind. So therefore, from the both perspective in the other modalities and the neuroscience, so if we want to build not only sensing but deeper understanding of the world using wireless signals, so generative model are a necessary step. So this is why starting last year, we put more effort into the RF-oriented generative model. So of course, it is not easy to build generative models for wireless signal. So here I list some challenges. So RF data are very different from the image data. So the first challenge is RF data is time series. So RF signals capture the dynamic details over time, unlike the static snapshot. Second, it is frequency domain. Essential features such as the DFS are embedded in the frequency domain. And the third, the RF data is complex valued. So both amplitude and the phase carry critical information. So we design a generative diffusion process that is better aligned with the various signal. So we call it RF diffusion. That is the diffusion process for radio frequency signals. So we know that for the diffusion model, there are two processes, the forward process and the reverse process. So in the forward process, we generate degradations that target both time and frequency. So on one hand, similar to the standard diffusion models, so we gradually add Gaussian noise into the time domain. So on the other hand, we also apply Gaussian blurs in the frequency domain. So the purpose is simple. Since a diffusion model learns how to recover the original signals from a degraded one, so we deliberately destroy both temporal and spectral structures. So the model has to learn to restrict the signal from time and frequency perspectives at the same time. So this is a basic idea of RF diffusion. So if you write the forward process in mathematical form, so it looks like that. So at each step, so we iteratively add the noise into the time domain and the frequency domain. So let me skip the formula here. So in the reverse process, we train a neural network to estimate each reverse step, that is to predict x t-1 from xt. So formally, we minorize the KL divergence between two transition probability. So after multiple steps, we can gradually recover the original signal distribution from the noise, the whole noise. So on the network side, we propose the hierarchical diffusion transformer. So it has two key aspects. So first, the architecture uses a two-stage structure. It appears, it separates denoising and deblurring into two sub-stages, so which make learning simpler. So second, the whole network is designed in the complex domain. So from the attention to feed-forward layer, all models support complex operations, so we can model complex value RF signals directly. So we use complex valued transformer blocks, including complex attention and complex feed-forward networks. So traditional neural network work on real numbers, but the physical layer of various signals are complex valued. That is both real and imaginary parts or the magnitude or phase. So we adopt complex valued neural network structures, which process real and imaginary parts together in each operation. So for example, a complex linear layer can be seen as the four real multiplications, so real to real, imaginary to imaginary, real to imaginary, and imaginary to real. So in this attention mechanism, we also adjust the computation. So transpose become Hermitian transpose, and the results are normalized in magnitudes while preserve the phase. So in the end, we get the network that is consistent with standard attention, but also preserves the complex structure of RF signals. So we evaluate our model in two signal types, so Wi-Fi and FMCW radar. So our generation is done at the raw signal level, but for visualization, we show the spectrogram. So for Wi-Fi, we compare DFS spectrogram. So for FMCW radar, we compare the range velocity spectrogram, so which are commonly used in wireless sensing. So we can see that samples generated by our RF diffusion model are much sharper, so with finer bind, thanks to the time frequency design. So to further test the usefulness of our model, so we use it to synthesize new data and expand the training site, so do the data augmentation. So this figure shows the pipeline. So we first train a generative model on existing real data, and then we let it generate more new samples. So finally, we mix the real and the generated data and use them together to train downstream models. Okay, we run the experiment on two Wi-Fi gesture recognition systems, VIDAR and EI. So in cross-domain settings, the accuracy of VIDAR and EI increased by 4.7% and 11.5% respectively. So in the same domain settings, the accuracy also improves. So we also find that, so if the generative model is of the low quality synthesized data can even hurt the performance. So a high quality generative model is not only helpful, but can have a decisive impact on the downstream tasks. So besides generating more samples, so we can also let the generative model directly generate the result. So here we show a classic communication task, the channel estimation. So we know that the uplink CSI, and we want to predict or estimate the downlink CSI. So we find that if we treat the uplink CSI as a conditional input, generative models include our RF diffusion can generate accurate predictions of download CSI. So here is the results. So the figure shows the estimation results. The blue line is the input uplink CSI, and the original line is the ground truth downlink CSI. So in recent years, large language models have become very popular. So NLP researchers have realized that so one generalized LLM can handle many different downstream tasks after light fine-tuning. So we have a neutral idea, since both language and the wireless signals are sequences. So can we use an LLM as a backbone for wireless sensing? So more specifically, we want to freeze the LLM backbone and only train a small set of adapter parameters. So in this way, we hope the transfer pairs from the language domain to the RF domain and build a unified multitask wireless sensing framework. So concretely, first we need to align the modalities. So CI is a complex value sequence, so we cannot feed it directly into the LLM. So we split the real and the imaginary parts, apply simple feature transformers, and make the two streams aligned. So then we map them into sequence embeddings that is LLM can understand. So this is like turning RF signals into the embedding in the LLM's input space. So on top of this, we notice that the different wireless tasks share some common patterns, but also have differences. For example, for detection, gesture recognition, and gait analysis, all involve motions of the torso, hands, and legs, but with different emphasis. So we design an expert routing module similar to the mixture of expert, this technology. As we move from the discriminative models to the generative models, so data becomes a major bottleneck for the field. So now we want to discuss some data sets and the simulation. So in CV and NLP, so one key reason for their rapid progress of large models is the availability of a large and high quality and public data set. So data sets like ImageNet, COCO, and other large text counterparts are the infrastructure of deep learning. So to address this problem, so we released a dataset called VIDA3 dataset. So it focuses on Wi-Fi gesture recognition. So the dataset includes 256,000 gesture instances, and it's about more than 8,000 minutes of data samples and from 75 different environments. So this dataset is the basis of many of our work and others' work, and is open to the community. However, as the models become larger, so manual data collection is not enough. So in robotics, so people have started to use the physical simulator plus LLM, such as the Genesis platform. So it has general physical engines as the core and LLM-based agent on top. So this agent can take neutral language descriptions and turn them into the scene configurations and parameters for the simulator. So this gives us an idea. So can we build a similar simulation platform for wireless sensing? So can we let LLM generate scenes, so behaviors and configurations automatically and greatly reduce manual efforts? So here is our solution. So based on this idea, so we are doing some early explorations. So our goal is to so multimodal LLM-driven wireless simulation platform. So the basic plan is that, so first we use the text descriptions to generate a 3D scene model, and then let a large model generate human actions such as fall, walk, so as time sequence. So finally, feed all this into a wireless simulator to generate the corresponding CSI or Doppler spectrogram. So this slide shows a demo of our work. So it's our attempt to try. So on the left is the scene model, and on the right is a real-time ray tracing view. We let a virtual person walk towards a sofa and interact with some objects in the environment. So during this process, various devices in the scene transmit and receive signals. So we can collect RF signals and correspond to the person's actions. So this shows the that using semantic prior from the large models to help wireless simulation is feasible. So in the end, we can turn the text knowledge of an LLM into the signal knowledge that can be used for train wireless models. So this will be one of our research directions in the near future. So Gen AI plus wireless is a very promising cross-discipline direction. So from an application perspective, generative AI can play many roles in wireless systems. It can be a key modeling method for channel estimation and signal noising. So it can also serve as a data augmentation or domain adaptation module to improve the generalization. So from a more fundamental viewpoint, so we believe that so generative models bring a paradigm shift. So traditional wireless systems are centered on the discriminative models. So from the sensing to the communication, the typical pattern is give the input and the output is a class label. So now with the generative model, we can see another way to solve the problem by learning how data are generated. So if we put all these ideas together, so they naturally arrive at the concept of a generative foundation model for wireless sensing. So first, in simulation environment, we can use self-supervised reconstruction to train a large generative model on massive data. So if this model can reconstruct daily RF signals well, it means that it has learned deep patterns behind the wireless data. So its internal representations should be captured and the essential structure of signals. So based on this, we can fine-tune the models for specific tasks and environments and use this intermediate representation as features. So this may allow us to perform various downstream tasks with higher accuracy, robustness, and generalization. So we believe this is a promising direction for the future. So finally, I would like to recommend some resources. So the first one is the WIDA 3 dataset, which I mentioned earlier. So we hope to see more researchers have their work built on this dataset. And second is our wireless sensing tutorial. It includes many signal processing codes and tools for wireless sensing. The goal is to help researchers from different areas and also students who are new to this topic and get started for wireless sensing. Third is the paper RF diffusion, which I have mentioned many times today. So it received the Best Artifact Award of Mobicom 2024 and passed the official reproducibility review. And we hope it can serve as a useful starting point for the future research. So here is some of the key references cited in this in my talk today. And the final words, so we believe that with the generative AI, wireless sensing can move from the single task discriminative sensing to a more unified and intelligent generative understanding. So that's all for my talk today. Thank you very much for your listening.
Thank you, Professor Ching Yang, for the presentation. For all the participants, if you have any question regarding the presentation, you may raise your hand.
Thanks, Professor Yang. Thanks for the insightful report. I have a question. Since your comprehensive...
Can you make louder, please?
Sorry. Thanks for the insightful presentation. Thanks, Professor Yang. And I have a question. Due to the comprehensive research, I have a question because it's very useful. So is there any applications of your research into some applications in daily life?
In daily life, okay.
Yeah.
So actually, I have shown several examples of the applications of wireless sensing. For example, in security and in healthcare and in human-computer interactions. Some of these applications are ready. I mean, the technology ready, and some of these have already a product like the wireless router and the commercial product to support this and go to the new generation of Wi-Fi standards. So, and I think they will come into our daily life in very near futures. So new Wi-Fi standards also adopt these features, these applications in the new standard. Okay.
Thank you, Professor Yang.
Thank you.
Maybe any other question?
Thank you, Professor Yang. It shows a clear timeline of wireless sensing development and your reflection and research on the development process. I benefit a lot from it. And because I'm not a researcher in this field, my question is how to integrate domain-specific knowledge into DNN design, and how did you and your students get the inspiration on it?
What design into the?
The DNN design for RF.
Oh, the DNDN for RF
Yes.
signals. Okay. And the second question is?
How did you and your students get the inspiration on it?
Oh, okay, thank you. So yes, you get the point, the important point that we tailored the traditional DNN models to the RF signals, right? So that's yes, because we are traditional people, so we use the traditional signal processing algorithms for the signal processing. But we see that, so for them, the CV community, computer vision community, so they don't use such a sophisticated features of images. They just use the end-to-end models, like CNN, end-to-end models. So our intuition is that, so if we know the signal processing algorithm, the rationale behind the algorithm, and we also know the reasonable way is end-to-end pipeline, so that we want to combine them together. So that is the intuition of our work, SLNet. So that in SLNet we get the SEN to make the spectrum enhancement. So actually, spectral enhancement is a traditional problem for wireless communication. And we also designed complex valued neural networks. Actually, this is a basic information for the traditional communication signal processing person, right? So that is we combine them. That is when we design our neural network, so we use the complex valued neural network. And when we design our neural network, we consider the spectrum enhancement question. That is our intuition.
Okay, once again, thank you so much, Professor Cheng Yong from Tsinghua University, China, for the presentation. We will now like to invite you to the stage to receive the certificate, which will be delivered by Professor Dr. Setin S.A. M.S.E. AKCA from Vice Rector of Academic Affairs, Research and Community Service. Ladies and gentlemen, we will now announce the best paper of MSN 2025. This award is presented to the authors of the paper entitled Generalization-Aware Distributed Minimax Optimization for Large-Scale Models on Research-Limited Devices. To present this award, we would like to invite the representative of the authors and also Insinyur Cindrawati Lesmana, MSc PhD IPU, to come forward. Congratulations to the winners. We would now like to have a group photo, ladies and gentlemen. Please move to the middle section for the photo as the picture will be taken from the stage. Please fill the empty seats on the middle section. Okay, everybody smile. 1, 2, 3. Cheese. Another one. Smile. 1, 2, 3. Okay, next one for the video. We gesture like this, and we say eyes on 3. Okay? Siap, udah? 1, 2, 3. Eyes. Thank you, everybody. A quick announcement before we have a snack break. We will have a coffee break before our parallel session, which is going to be held at Gedung B, 9th floor. Please enjoy the refreshment and feel free to ask the staff if you need assistance. Thank you so much.